So clearly one of the big challenges is that graphs are really big, okay, big, massive, really massive. You can add any kind of these fancy adjectives. And more importantly, just having the graphs getting larger, the queries that you fire on these graphs are getting more and more interesting and exciting and harder to evaluate. So one is, you can have the standard pattern like queries, which you can, all of you, I think some of you already said, it's similar to SQL with few joins. Yeah, SQL has joined, really done well for join queries. But you can actually go into a little more complicated things in these graphs and say, I want to do recursive traversals with unbounded recursion, right? I just want to keep doing reachabilities, right? Then I have no good solution which is really efficient, right? This is allowed in SPARQL extensions people are talking about. And then you have on these graphs many analytic queries that you can, I mean, all of you are already familiar with PageRank. PageRank is an analytic query which runs on the entire graph, tries to rank based on their random walk potentials, right? You can also think of, I'll first fire one query, get a subgraph out, some ad hoc subset of the entire LOD, and then from this I will extract dense subgraphs or some kind of K-core decomposition of this, or compute Steiner trees, right? If you are familiar with these keyword search and graphs, this is basically what they do. They fire some initial set of queries which will filter out certain nodes and then try to connect them up using Steiner trees. Again, these are not so easy to solve using relational databases. The solution most of the current approaches use is, let's take this graph and put it in memory and deal with it, okay? While it is a valid solution, given that the memory is getting cheaper, it's still not cheap enough to hold 30 billion triples, okay? So we need to come up with better strategies for dealing with it.
Is there a concept of frequent item sets and rules in the world of graphs?
Yes. So you can always look at frequent subgraphs, right? So in fact, there is another, as they say, some kind of.
But now your subgraphs are not just the structure. You're looking at now at the edges also.
So you can relax the labels on the edges and say, I don't care about the edges, but really any kind of structure. Or you can say, I will include just the labels, but I relax on the subjects and objects that are there. So people have worked on these kind of
frequent subgraphs. Then you can also have
interesting subgraphs, right? Just to reiterate my point, so far we have never talked about how exactly they are evaluated. So far I have never even mentioned how they are evaluated. So created, you can just create any graph in the good old way that you take your relational database, perform all your joins and store it as a graph, right? I mean, that's one cheap way of answering it. But in LOD world, there are so many efforts coming both from automated methods as well as from manually hand coding stuff. So if you go back and look at it, DBLP for example, they maintained huge records of which paper appeared in which conference, which journal, who are the authors and so on. And they again wrote scripts from this structured relational table they had to turn it into RDF and then give it out as Spark RDF data set, which is essentially a graph, right? So that's one method of doing it. Yago, Freebase kind of efforts, they're focusing on, Yago and DBpedia, are focusing more on, let's take some almost structured data like Wikipedia and apply whole bunch of machine learning tools, natural language processing tools, so that you can extract out these facts, X is related to Y in some way, and then put them into the graph form, right? And Psych again hand coded many of these knowledge. So there are many efforts in which the graphs were created. Again, I'm not going too much into any of those. I agree that these are challenges, but I'm looking at a slightly different challenge. So just to continue with this slide and try to finish it quickly, is that queries are richer, graphs are bigger, and you can say, hey, why not use some magic bullet like Hadoop, right? Google uses it on terabytes, so 30 billion should be cheap, right? But the problem is that your graphs are not the same as text tables, right? Text pieces, which Google uses this for. So your graphs have complex interconnectivity. This node is connected to God knows what other nodes, right? What kind of relationships are there? That's one. And today, some connections may not exist, but tomorrow, you can just add one edge. It seems like a very harmless piece of edge saying Dolph Lundgren and Bruce Willis acted in The Expendables. They never acted before. Suddenly, you put these two together and form a connection. So assume that in Hadoop you had actually partitioned it nicely. Dolph Lundgren is the guy who never works with Bruce Willis. I'll put them these two separately. And suddenly The Expendables comes, all your partitioning falls apart, right? Which is not the case in the application settings where Hadoop is used. Your partitioning is fine. You don't need to worry about it anymore. Your partitioning logic remains the same. But here, things can get really messy, even in a single static snapshot, as well as when you have these dynamism in your data set. So therefore, data partitioning solutions are also need rethinking. Okay, so given all that, it's not like I'm the only guy who has thought about it and preaching you. There is a whole bunch of people who have worked on it. Okay, there is huge research as well as industry work that's going on for developing graph data management tools for very different kind of applications, both generic as well as in the analytics world. So for example, there is transactional graph database systems, data management systems like Neo4j, Jina, HyperGraphDB, RDF-XXX. They really focus on these LOD kind of settings, right? Where until now, you never had analytics queries on them. You just had more edges coming in, a pattern, and you match it, right? But we are saying that now Sparkle is also getting richer with recursive reasoning kind of queries. Then transactional GDM has to evolve into which supports little more than just the transactional pattern matching queries. And then you had analytic GDM, analytic graph database management like Pregel and Giraffe, which can be seen as Hadoop style processing for graphs, which have recursive reasoning. You can compute PageRank using Pregel. In fact, this is the claim Pregel paper also makes, that they designed Pregel so that they can do PageRank on massive graphs. Pregel is not, but it's open source implementation which is on top of Hadoop called Giraffe. Giraffe is open.
Oh,
yeah, it's actually bad at this moment, but it's not as GraphLab. Yeah, GraphLab I haven't put it because it's not really a GDM style GDM. They are more designed for doing machine learning applications on top of some graphs without really worrying about. Yeah, exactly. So that's basically the focus.